Hi there, you're in the lab with your mate JJ. Today is new book teardown day. Today we're going to be tearing down a new book. My silly job title for today is Ohm Oracle, today on the Ohm Oracle. The book that we'll be tearing down is Electricity and Magnetism, 3rd edition, by Edward M. Purcell and David J. Morin. This is the sort of physics textbook that's referenced by Learning the Art of Electronics. So that's where I heard about this book, and I bought it because it was in the references from that. So today what we're going to be doing is just popping over to the bench here and having a look through this book and seeing what's inside it. We won't be looking in super close detail. We'll just sort of be flipping through and taking stock of what's in there. So let's jump over to the bench and have a look at what's in this thing. Here we are on the bench, and this is our book. On the front, title, Electricity and Magnetism, 3rd edition, Edward M. Purcell and David J. Morin. Published by Cambridge, it says Cambridge. So, some praise on the back. Let's have a look at that. This is from David Derby's University of Chicago Laboratory Schools. David Morin has brought Purcell's beautiful book up to date with a long prayed for gentle revision of this legendary work into everyday SI units, adding new material and citations to recent research. And if that were not enough, Morin, a connoisseur of problems, enriches this new edition with a bounty of challenging and fascinating exercises. All right. And then Peter Krager, University of Toronto, says, with the update to SI units and the addition of numerous worked examples and problems, this modernized version of Purcell's classic text should serve to re-establish for a new generation of students its well-deserved reputation as one of the finest and most popular undergraduate E&M texts ever written. Wow, high praise. And Daniel V. Schroeder from Weber State University says, Purcell's book taught a whole generation of physicists that you needn't travel at half the speed of light to see relativity in action. Magnetism is caused by length contraction. Radiation is a consequence of the cosmic speed limit. This welcome revision will bring these insights and many others to a new generation. All right. This classic textbook introduces students to the world of electricity and magnetism. Covering all the standard introductory topics, this 3rd edition is revised and updated by David Morin, who now uses SI units. Students are supported by worked examples throughout the text and over 200 solved end-of-chapter problems. A further 350 homework exercises help develop and test students' understanding. Applications at the end of each chapter demonstrate how the concepts relate to the real world. A complete solutions manual for adopting instructors is available at cambridge.org/Purcell-Morin. Published by Cambridge University Press, www.cambridge.org. There you go. Now, we've got some we've got some cheat sheets in the front and in the back. So what have we got? We've got derived units. The Newton is kilogram meters per second squared. And the joule is the Newton meter, which is kilogram meter squared per second squared. The ampere is coulombs per second. The volt is joules per coulomb, or kilogram meters squared per coulomb second squared. Wow. The farad, coulombs per volt. The ohm, volts per amp. The watt, joule per second. And the Tesla, Newton per coulomb meter per second. That doesn't seem quite right, does it? Because That's S for second, and C for Coulomb. Oh, Newton. Oh, okay, so they must cancel some. I don't want to think too hard about that. Tesla's beyond my pay grade. And the Henry, volts per amp per second. Then we've got Maxwell's equations, something which I don't understand very well yet at all. Curl E equals negative. I don't know. I don't know that. Is it D? Do you call it D? I'm not sure. My calculus isn't that good yet. Is it a partial differential? I'm not sure. Anyway, that's them, Maxwell's equations. They're a whole thing for me to learn. I've heard of them. I don't know how they work. Fundamental constants. Okay. So we've got the speed of light, elementary charge. That's the charge of an electron. Electron mass, proton mass, Avogadro's number, Boltzmann constant, Planck constant, gravitational constant, electron magnetic moment, proton magnetic moment, permittivity of free space, and permeability of free space. And then we've got a thing called the divergence theorem, Stokes theorem, and gradient theorem. All of this stuff is just beyond me. It's a little blurb in the front here. We might as well read that. Electricity and magnetism. For 50 years, Edward M. Purcell's classic textbook has introduced students to the world of electricity and magnetism. This third edition has been brought up to date and is now in SI units. It features hundreds of new examples, problems, and figures, and contains discussions of real-life applications. The textbook covers all the standard introductory topics, such as electrostatics, magnetism, circuits, electromagnetic waves, and electric and magnetic fields in matter. Taking a non-traditional approach, magnetism is derived as a relativistic effect. Mathematical concepts are introduced in parallel with the physical topics at hand, making the motivations clear. Macroscopic phenomena are derived rigorously from the underlying microscopic physics. With worked examples, hundreds of illustrations, and nearly 600 end-of-chapter problems and exercises, this textbook is ideal for electricity and magnetism courses. Solutions to the exercises are available for instructors at cambridge.org/Purcell Morin. Edward M. Purcell, 1912 to 1997, was the recipient of many awards for his scientific, educational, and civic work. In 1952, he shared the Nobel Prize for Physics for the discovery of nuclear magnetic resonance in liquids and solids, an elegant and precise method of determining the chemical structure of materials that serves as the basis for numerous applications, including magnetic resonance imaging, MRI. During his career, he served as science advisor to Presidents Dwight D. Eisenhower, John F. Kennedy, and Lyndon B. Johnson. David J. Morin is a lecturer and the Associate Director of Undergraduate Studies in the Department of Physics, Harvard University. He is the author of the textbook Introduction to Classical Mechanics, published by Cambridge University Press in 2008. Off we go. So I think we'll read the prefaces. But we'll read the table of contents first. So there's a preface to the third edition, a preface to the second edition, and a preface to the first edition. Then there's chapter 1, electrostatics, charges and fields, electric charge, conservation of charge, quantization of charge, Coulomb's law, energy of a system of charges, electrical energy in a crystal lattice, the electric field, charge distributions, flux, Gauss's law, field of a spherical charge distribution, field of a line charge, field of an infinite flat sheet of charge, the force on a layer of charge, energy associated with the electric field, applications, chapter summary, problems, exercises. Chapter 2, the electric potential, line integral of the electric field. potential differences and the potential function, gradient of a scalar function, derivation of the field from the potential, potential of a charge distribution, uniformly charged disk, dipoles, divergence of a vector function, Gauss's theorem and the differential form of Gauss's law, the divergence in Cartesian coordinates, the Laplacian, Laplace's equation, distinguishing the physics from the mathematics, the curl of a vector function, Stokes' theorem, the curl in Cartesian coordinates, the physical meaning of the curl, applications, chapter summary, problems, exercises. Chapter 3, electric fields around conductors, conductors and insulators, conductors and the electrostatic field, the general electrostatic problem and the uniqueness theorem, image charges, capacitance and capacitors, potentials and charges on several conductors, energy stored in a capacitor, other views of the boundary value problem, applications, chapter summary, problems, exercises. Chapter 4, electric currents, electric current and current density, steady currents and charge conservation, electrical conductivity and Ohm's law, the physics of electrical conduction, conduction in metals, semiconductors, circuits and circuit elements, energy dissipation in current flow, electromotive force and the voltaic effect and the voltaic cell, networks with voltage sources, variable currents in capacitors and resistors, application, chapter summary, problems, exercises. Chapter 5, the fields of moving charges. From Ørsted to Einstein, magnetic forces, measurement of charge in motion, invariance of charge, electric field measured in different frames of reference, field of a point charge moving with constant velocity, field of a charge that starts or stops, force on a moving charge, interaction between a moving charge and other moving charges. Chapter summary, problems, exercises. Chapter 6, the magnetic field. Definition of the magnetic field, some properties of the magnetic field. Vector potential, field of any current carrying wire, fields of rings and coils, change in B at a current sheet, how the fields transform, Rowland's experiment, electrical conduction in a magnetic field, the Hall effect, applications, chapter summary, problems, exercises. Chapter 7, electromagnetic induction, Faraday's discovery, conducting rod moving through a uniform magnetic field, loop moving through a non-uniform magnetic field, stationary loop with the field source moving, universal law of induction, mutual inductance, a reciprocity theorem, self-inductance, circuit containing self-inductance, energy stored in the magnetic field, applications, chapter summary, problems, exercises. Chapter 8, alternating current circuits, a resonant circuit, alternating current, complex exponential solutions, alternating current networks, admittance and impedance, power and energy in alternating current circuits, applications, chapter summary, problems, exercises. Chapter 9, Maxwell's equations and electromagnetic waves. Something is missing. The displacement current, Maxwell's equations, an electromagnetic wave, other waveforms, superposition of waves, energy transport by electromagnetic waves, how a wave looks in a different frame, applications, chapter summary, problems, exercises. Chapter 10, electric fields in matter, dielectrics, the moments of a charge distribution, the potential and field of a dipole, the torque and the force on a dipole in an external field, Atomic and molecular dipoles induce dipole moments. Permanent dipole moments. The electric field caused by polarized matter. Another look at the capacitor. The field of a polarized sphere. A dielectric sphere in a uniform field. The field of a charge in an electric medium and Gauss's law. A microscopic view of the dielectric. Polarization in changing fields. The bound charge current. An electromagnetic wave in a dielectric. Applications, chapter summary, problems, exercises. Chapter 11, magnetic fields in matter. How various substances respond to a magnetic field. The absence of magnetic charge. The field of a current loop. The force on a dipole in an external field. Electric currents in atoms. Electron spin and magnetic moment. Magnetic susceptibility. The magnetic field caused by magnetized matter. The field of a permanent magnet. Free currents and the field H. Ferromagnetism, applications, chapter summary, problems, exercises. Chapter 12, solutions to the problems. Solutions for chapters 1 through 11. Appendix A, differences between SI and Gaussian units. Appendix B, SI units of common quantities. Appendix C, unit conversions. Appendix D, SI and Gaussian formulas. Appendix E, exact relations among SI and Gaussian units. Appendix F, curvilinear coordinates. Appendix G, a short review of special relativity. Appendix H, radiation by an accelerated charge. Appendix I, superconductivity. Appendix J, magnetic resonance. Appendix K, helpful formulas and facts. Then we've got references on page 831 and the index begins on page 833. I thought I might read the prefaces in order of publication. So let's do the preface to the first edition of volume 2. We'll do that first. So this is the preface to the first edition, and it was written by Purcell, but it doesn't say when. The subject of this volume of the Berkeley Physics course is electricity and magnetism. By the way, this Berkeley Physics course was like a planned project. It was going to have a bunch of books in it on different physics topics, and in the end, this book sort of stood alone rather than with the Berkeley Physics course. Anyway, the subject of this volume of the Berkeley Physics course is electricity and magnetism. The sequence of topics in rough outline is not unusual. Electrostatics, steady currents, magnetic field, electromagnetic induction, electric and magnetic polarization in matter. However, our approach is different from the traditional one. The difference is most conspicuous in chapters 5 and 6, where, building on the work of volume 1, we treat the electric and magnetic fields of moving charges as manifestations of relativity and the invariance of electric charge. This approach focuses attention on some fundamental questions such as charge conservation, charge invariance, the meaning of field. The only formal apparatus of special relativity that is really necessary is the Lorentz transformation of coordinates and the velocity addition formula. It is essential, though, that the student bring to this part of the course some of the ideas and attitudes Volume 1 sought to develop. Among them, a readiness to look at things from different frames of reference, an appreciation of invariance, and a respect for symmetry arguments. We make much use also in Volume 2 of arguments based on superposition. Our approach to electric and magnetic phenomena in matter is primarily microscopic, with emphasis on the nature of atomic and molecular dipoles, both electric and magnetic. Electric conduction also is described microscopically in the terms of a Drude-Lorentz module. Naturally, some questions have to be left open until the student takes up quantum physics in Volume 4. But we freely talk in a matter-of-fact way about molecules and atoms as electrical structures with size, shape, and stiffness, about electron orbits and spin. We try to treat carefully a question that is sometimes avoided and sometimes beclouded in introductory texts: the meaning of the macroscopic fields B, E, and B inside a material. In Volume 2, the student's mathematical equipment is extended by adding some tools of the vector calculus: gradient, divergent, curl, and the Laplacian. These concepts are developed as needed in the early chapters. In its preliminary versions, Volume 2 has been used in several classes at the University of California. It has benefited from criticism by many people connected with the Berkeley course, especially from contributions by E.D. Commons and F.S. Crawford Jr., who taught the first classes to use the text. They and their students discovered numerous places where clarification or something more drastic was needed. Many of the revisions were based on their suggestions. Students' criticisms of the last preliminary version were collected by Robert Morin, who also helped to organize the problems. Valuable criticism has come also from J.D. Govender, who used the preliminary version at the University of Texas, and from E.F. Taylor of Wesleyan University. Ideas were contributed by Alan Kaufman at an early stage of the writing. A. Felser worked through most of the first draft as our first test student. The development of this approach to electricity and magnetism was encouraged not only by our original course committee, but by colleagues active in a rather parallel development of new course material at the Massachusetts Institute of Technology. Among the latter, J.R. Tessman of the MIT Science Teaching Center and Tufts University was especially helpful and influential in the early formulation of the strategy. He has used the preliminary version in class at MIT, and his critical readings of the entire text has resulted in many further changes and corrections. Publication of the preliminary version and its successive revisions was supervised by Mrs. Mary R. Maloney. Miss Leela Lau typed most of the manuscript. The illustrations were put into final form by Felix Cooper. The author of this volume remains deeply grateful to his friends in Berkeley, and most of all to Charles Kittel, for the stimulation and constant encouragement that have made the long task enjoyable. There you go. So that was the preface to the first edition. So now let's get the preface to the second edition. It's like, oh no, it's a couple of pages. Yeah. All right, this is again from Edward M. Purcell, the second edition. This revision of Electricity and Magnetism, Volume 2 of the Berkeley Physics course, has been made with three broad aims in mind. First, I have tried to make the text clearer at many points. In years of use, teachers and students have found innumerable places where a simplification or reorganization of an explanation could make it easier to follow. Doubtless some opportunities for such improvements still have been missed. Not too many, I hope. A second aim was to make the book practically independent of its companion volumes in the Berkeley Physics course. As originally conceived, it was bracketed between Volume 1, which provided the needed special relativity, and Volume 3, Waves and Oscillations, to which was allocated the topic of electromagnetic waves. As it has turned out, Volume 2 has been rather widely used alone. In recognition of that, I have made certain changes and additions. A concise review of the relations of special relativity is included as Appendix A. Some previous introduction to relativity is still assumed. The review provides a handy reference and summary for the ideas of formulas we need to understand the fields of moving charges and their transformation from one frame to another. The development of Maxwell's equations for the vacuum has been transferred from the heavily loaded Chapter 7 on induction to a new Chapter 9, where it leads naturally into an elementary treatment of plain electromagnetic waves, both running and standing. The propagation of a wave in a dielectric medium can then be treated in Chapter 10 on electric fields in matter. A third need to modernize the treatment of certain topics was most urgent in the chapter on electrical conduction. A substantially rewritten Chapter 4 now includes a section on the physics of homogeneous semiconductors, including doped semiconductors. Devices are not included, not even a rectifying junction, but what is said about bands and donors and acceptors could serve as starting point for development of such topics by the instructor. Thanks to solid-state electronics, the physics of the voltaic cell has become even more relevant to daily life as the number of batteries in use approaches in order of magnitude the world's population. In the first edition of this book, I unwisely chose as the example of an electrolytic cell the one cell, the Western Standard Cell, which advances in physics were soon to render utterly obsolete. That section has been replaced by an analysis with new diagrams of the lead-acid storage battery, ancient, ubiquitous, and far from obsolete. One would hardly have expected that, in the revision of an elementary text in classical electromagnetism, attention would have to be paid to new developments in particle physics. But that is the case for two questions that were discussed in the first edition: the significance of charge quantization and the apparent absence of magnetic monopoles. Observation of proton decay would profoundly affect our view of the first question. Assiduous searches for that, and also for magnetic monopoles, have at this writing yielded no confirmed events, but the possibility of such fundamental discoveries remains open. 3 special topics, optional extensions of the text, are introduced in short appendices. Appendix B, radiation by an accelerated charge, and Appendix C, superconductivity, and Appendix D, magnetic resonance. Our primary system of units remains the Gaussian CGS system. The SI units, ampere, coulomb, volt, ohm, and Tesla, are also introduced in the text and used in many of the problems. Major formulas are repeated in their SI formulation with explicit directions about units and conversion factors. The charts inside the back cover summarize the basic relations in both systems of units. A special chart in Chapter 11 reviews, in both systems, the relations involving magnetic polarization. The student is not expected or encouraged to memorize conversion factors, though some may become more or less familiar through use, but to look them up whenever needed. There is no objection to a mixed unit like the ohm centimeter, still often used for resistivity, providing its meaning is perfectly clear. The definition of the meter in terms of an assigned value for the speed of light, which has just become official, simplifies the exact relations among units, as briefly explained in Appendix E. There are some 300 problems, more than half of them new. It is not possible to thank individually all the teachers and students who have made good suggestions for changes and corrections. I fear that some will be disappointed to find that their suggestions have not been followed quite as they intended. That the net result is a substantial improvement, I hope most readers familiar with the first edition will agree. Mistakes both old and new will surely be found. Communications pointing them out will be greatly received. It is a pleasure to thank Olive S. Rand for her patient and skillful assistance in the production of the manuscript. All right, so that was the preface to the second edition. And now this is the preface to the third edition, and was written by David Morin. Let's take a quick break. Preface to the third edition of Volume 2. When they say Volume 2, they mean the second volume of the Berkeley stuff. But anyway, that's this book that they're talking about. For 50 years, physics students have enjoyed learning about electricity and magnetism through the first 2 editions of this book. The purpose of the present edition is to bring certain things up to date and to add new material in the hopes that the trend will continue. The main changes from the section from the second edition. 1, the conversion from Gaussian units to SI units, and 2, the addition of many solved problems and examples. The first of these changes is due to the fact that the vast majority of courses on electricity and magnetism are now taught in SI units. The second edition fell out of print at one point, and it was hard to watch such a wonderful book fade away because it wasn't compatible with the way the subject is presently taught. Of course, there are differing opinions as to which system of units is better for an introductory course, but this issue is moot given the reality of these courses. For students interested in working with Gaussian units, or for instructors who want their students to gain exposure to both systems, I have created a number of appendices that should be helpful. Appendix A discusses the differences between the SI and Gaussian systems. Appendix C derives the conversion factors between the corresponding units in the two systems. Appendix D explains how to convert formulas from SI to Gaussian, and then it lists side by side the SI and Gaussian expressions for every important result in the book. A little time spent looking at this appendix will make it clear how to convert formulas from one system to the other. The second main change in the book is the addition of many solved problems and also many new examples in the text. Each chapter ends with problems and exercises. The solutions to the problems are located in chapter 12. The only official differences between the problems and the exercises is that the problems have solutions included, whereas the exercises do not. A separate solutions manual for the exercises is available to instructors. In practice, however, one difference is that some of the more theorem-ish results are presented in the problems so that students can use these results in other problems and exercises. Some advice on using the solutions to the problems. Problems and exercises are given a very subjective difficulty rating from 1 star to 4 stars. If you are having trouble solving a problem, it is critical that you don't look at the solution too soon. Brood over it for a while. If you do look at the solution, don't just read it through. Instead, cover it up with a piece of paper and read one line at a time until you reach a hint to get you started. Then set the book aside and work things out for real. That's the only way it will sink in. It's quite astonishing how unhelpful it is simply to read a solution. You'd think it would do some good, but in fact it is completely ineffective in raising your understanding to the next level. Of course, a careful reading of the text, including perhaps a few problem solutions, is necessary to get the basics down. But if level 1 is understanding the base concepts and level 2 is being able to apply those concepts, then you can read and read until the cows come home and you'll never get past level 1. The overall structure of the text is essentially the same as in the second edition, although a few new sections have been added. Section 2.7 introduces dipoles. The more formal treatment of dipoles, along with their applications, remains in place in Chapter 10. But because the fundamentals of dipoles can be understood using only the concepts developed in Chapters 1 and 2, it seems appropriate to cover this subject earlier in the book. Section 8.3 introduces the important technique of solving differential equations by forming complex solutions and then taking the real part. Section 9.6.2 deals with the pointing vector, which opens up the door to some very cool problems. Each chapter concludes with a list of everyday applications of electricity and magnetism. The discussions are brief. The main purpose of these sections is to present a list of fun topics that deserve further investigation. You can carry onward with some combination of books, internet, people pondering. There is effectively an infinite amount of information out there. See the references at the beginning of section 116 for some starting points. So my goal in these sections is simply to provide a springboard for further study. The intertwined nature of electricity, magnetism, and relativity is discussed in detail in Chapter 5. Many students find this material highly illuminating, although some find it a bit difficult. However, these two groups are by no means mutually exclusive. For instructors who wish to take a less theoretical route, it is possible to skip directly from Chapter 4 to Chapter 6 with only a brief mention of the main result from Chapter 5, namely the magnetic field due to a straight current carrying wire. The use of non-Cartesian coordinates, cylindrical, spherical, is more prominent in the present edition. For setups possessing certain symmetries, a wisely chosen system of coordinates can greatly simplify the calculations. Appendix F gives a review of the various vector operators in the different systems. Compared with the second edition, the level of difficulty of the present edition is slightly higher due to a number of hefty problems that have been added. If you are looking for an extra challenge, these problems should keep you on your toes. However, if these are ignored, which they certainly can be in any standard course using this book, then the level of difficulty is roughly the same. I am grateful to all the students who used a draft version of this book and provided feedback. Their input has been invaluable. I would also like to thank Jacob Barandes for many illuminating discussions of the more subtle topics in the book. Paul Horowitz helped. There we go, Paul Horowitz. Paul Horowitz helped get the project off the ground and has been an endless supplier of cool facts. It was a pleasure brainstorming with Andrew Milowski, who offered many ideas for clever new problems. Howard Georgie, Wolfgang Ruckner provided much appreciated sounding boards and sanity checks. Takayuya Kitagawa carefully read through a draft version and offered many helpful suggestions. I thank Ali Wulat and Irene Pizzi for their professional work in producing the layout of the book and copy editing the manuscript. And then a whole bunch of other people are thanked. Despite careful editing, there is zero probability the book is error-free. A great deal of new material has been added and errors have been undoubtedly crept in. If anything looks amiss, please check the webpage for a list of typos, updates, etc. And please let me know if you discover something that isn't already posted. Suggestions are always welcome. All right, so that was all of the prefaces. I think I might get a coffee before we take on the rest of the book. I'll just be back in a sec. Electrostatics, charges and fields. Overview. The existence of this book is owed, both figuratively and literally, to the fact that the building blocks of matter possess a quality called charge. Two important aspects of charge are conservation and quantization. The electric force between two charges is given by Coulomb's law. Like the gravitational force, the electric force falls off like 1 on r squared. It is conservative, so we can talk about the potential energy of a system of charges, the work done in assembling them. A very useful concept is the electric field, which is defined as the force per unit charge. Every point in space has a unique electric field associated with it. We can define the flux of the electric field through a given surface. This leads us to Gauss's law, which is an alternative way of stating Coulomb's law. In cases involving sufficient symmetry, it is much quicker to calculate the electric field via Gauss's law than via Coulomb's law and direct integration. Finally, we discuss the energy density in the electric field, which provides another way of calculating the potential energy of a system. Electric charge, conservation of charge, quantization of charge. There's a box here. The total electric charge in an isolated system, that is, the algebraic sum of the positive and negative charges present at any time, never changes. Okay. Just that again, that's the total electric charge in an isolating system never changes. The algebraic sum just means the positive and negative are taken into account. Coulomb's law. So we can state this compactly in vector form like this. F2 equals K Q1 Q2 R21 2, 1 squared. Oh man, I've got all this math that I'm going to need to learn. Not going to learn it today though, and energy of a system of charges. Electrical energy in a crystal lattice. The electric field. Charge distributions. Each element of the charge distribution, I don't know, that P, is that rho? I'm not sure, let me check. Yeah, that's rho, but I don't know what it means. Maybe it's the charge distribution. I'm not sure. Flux. The relation between the electric field and its sources can be expressed in a remarkably simple way, one that we shall find very useful. For this, we need to define a quantity called flux. Oh man, just had a phone call from an old friend. So I've just been on the phone for an hour or two. I forget what we're up to. I think we were talking about flux. The relation between the electric field and its sources can be expressed in a remarkably simple way, one that we shall find very useful. For this, we need to define a quantity called flux. Consider some electric field in space, and in this space some arbitrary closed surface, like a balloon of any shape. Figure 115 shows such a surface. The field being suggested by a few field lines. Now divide the whole surface into little patches that are so small that over any one patch the surface is practically flat and the vector field does not change appreciably from one part of a patch to another. In other words, don't let the balloon be too crinkly and don't let its surface pass right through a singularity. There's a note here about singularity. By a singularity of the field, we would ordinarily mean not only a point source where the field approaches infinity, but also any place where the field changes magnitude or direction discontinuously, such as an infinitesimally thin layer of concentrated charge. Actually, this latter, milder kind of singularity would cause no difficulty here unless our balloon's surface were to coincide with the surface of discontinuity over some finite area. Okay. In other words, don't let the balloon and don't let its surface pass right through a singularity of the field, such as a point charge. The area of a patch has a certain magnitude in square meters, and a patch defines a unique direction, the outward pointing normal to its surface. Since the surface is closed, you can tell its inside from its outside. There is no ambiguity. Let this magnitude and direction be represented by a vector. Then, for every patch into which the surface has been divided, such as patch number J, we have a vector AJ giving its area and orientation. The steps we have just taken are pictured in figures 115b and c. Note that the vector AJ does not depend at all on the shape of the patch. It doesn't matter how we have divided up the surface as long as the patches are small enough. Let EJ be the electric field vector at the location of patch number J. The scalar product EJ times AJ is a number. We call this number the flux through that bit of surface. To understand the origin of the name, imagine a vector function that represents the velocity of motion in a fluid, say in a river, where the velocity varies from one place to another, but is constant in time at any one position. Denote this vector field by V, measured in meters per second. Then if A is the oriented area in square meters of a frame lowered into the water, VA is the rate of flow of water through the frame in cubic meters per second. The cos theta factor in the standard expression for the dot product correctly picks out the component of V along the direction of A, or equivalently, the component of A along the direction of V. We must emphasize that our definition of flux is applicable to any vector function, whatever physical variable it may represent. Now let us add up the flux through all the patches to get the flux through the entire surface. A scalar quantity which we shall denote by, well, what is that? Is that theta or phi? I think it's capital phi. All right, and then they're taking the sum for all j of EJ times AJ. Letting the patches become smaller and smaller and more numerous without limit, we pass from the sum in equation 1.5 to a surface integral. So the integral of E times E dA. Okay. A surface integral of any vector function f over a surface S means just this. Divide S into small patches, each represented by a vector outward of magnitude equal to the patch area at every patch. Take the scalar product of the patch area vector and the local f. Sum all these products, and the limit of this sum, as the patches shrink, is the surface integral. Do not be alarmed by the prospect of having to perform such a calculation for an awkwardly shaped surface like in figure 115. The surprising property we are about to demonstrate makes this unnecessary. Okay, and I'm going to assume that's Gauss's law. Let's keep reading. Take the simplest case imaginable. Suppose the field is that of a single isolated positive charge Q, and the surface is a sphere of radius R centered on the point charge. What is the flux through this surface? The answer is easy because the magnitude of E at every point on the surface is Q divided by 4 pi epsilon 0 R squared. And epsilon 0, that was the permittivity of free space. And its direction is the same as that of the outward normal at that point. So we have phi equals E times total area equals Q divided by 4 pi epsilon 0 R squared times 4 pi R squared equals Q divided by epsilon 0. Well, that simplified a lot, didn't it? The flux is independent of the size of the sphere. Here, for the first time, we see the benefit of including the factor 1 on 4 pi in Coulomb's law in equation 1.4. Without this factor, we would have an uncancelled factor of 4 pi in equation 127, and therefore also eventually in one of Maxwell's equations. Indeed, in Gaussian units, equation 127 takes the form of phi equals 4 pi q. Now imagine a second surface or balloon enclosing the first, but not spherical, as in figure 118. We claim that the total flux throughout this surface is the same as that throughout the sphere. To see this, look at a cone radiating from Q that cuts a small patch A out of the sphere and continues onto the other surface, where it cuts out a patch A at a distance R from the point charge. The area of the patch capital A is larger than that of the patch lowercase a by 2 factors. First, by the ratio of the distance squared, and second, owing to its inclination by the factor 1 on cos theta. The angle theta is the angle between the outward normal and the radial direction, see figure 118. The electric field in that neighborhood is reduced from its magnitude on the sphere by a factor of R divided by R squared, and is still radially directed, letting ER be the field at the outer patch and ER be the field at the space. We have flux through the outer patch equals this expression, flux through the inner patch equals this expression. Using the above facts concerning the magnitude of R in the area of A. The flux through the outer patch can be written as this, which equals the flux through the inner patch. Now every patch on the outer surface can in this way be put into correspondence with part of the spherical surface, so the total flux must be the same through the two surfaces. That is, the flux through the new surface must be just Q divided by the permittivity of free space. But this was a surface of arbitrary shape and size. There's a note here. To be sure, we had the second surface enclosing the sphere, but it didn't have to, really. Besides, the sphere can be taken as small as we please. We conclude the flux of the electric field through any surface enclosing a point charge Q is Q divided by epsilon naught. As a corollary, we can say that the total flux through a closed surface is zero if the charge lies outside the surface. We leave the proof of this to the reader along with figure 119 as a hint of one possible line of argument. There's a box here. The flux of the electric field E through any closed surface, that is the integral of E dA over the surface, equals 1 divided by epsilon naught times the total charge enclosed by the surface. So the integral of E dA equals 1 on epsilon naught times the sum of Qi for all I equals 1 on epsilon naught times the integral of, is that rho again, to V? Okay, this is Gauss's law, which we heard about. Now it's getting too hard for me. Field of a spherical charge distribution. Field of a line charge. Field of an infinite flat sheet of charge. That's an interesting idea. The force on a layer of charge. Energy associated with the electric field. Applications. Each chapter of this book concludes with a list of everyday application of the topics covered in the chapter. The discussions are brief. It would take many pages to explain each item in detail. Real-life physics tends to involve countless variations, complications, and subtleties. The main purpose here is just to say a few words to convince you that the applications are interesting and worthy of further study. You can carry onward with some combination of books, internet, people, pondering. There is effectively an infinite amount of information out there, so you should take advantage of it. 2 books packed full of real-life applications are The Flying Circus of Physics by Walker in 2007 and How Things Work by Bloomfield 2010. And some very informative websites are the Flying Surface of Physics website and howstuffworks.com. I'm not sure if those websites are still around. Shall we have a look? I might as well have a look. All right, well, I'll put the links to those 4 websites in the show notes. The Flying Circus of Physics doesn't seem to be there anymore, but I found it at thearchive.org. And How Stuff Works is there. Explain That Stuff is there. And of course, Wikipedia is still there. It says these websites can point you to more technical sources if you want to pursue things at a more advanced level. With the exception of the gravitational force keeping us on Earth and ignoring magnets for the time being, essentially all everyday forces are electrostatic in origin, with some quantum mechanics mixed in to make things stable. See Earnshaw's theorem in section 212. Friction, tension, normal force, etc. all boil down to the electric forces between the electrons in the various atoms and molecules. You can open a door by pushing on it because the forces between neighboring molecules in the door and also in your hand are sufficiently strong. We can ignore the gravitational force between everyday sized objects because the gravitational force is so much weaker than the electric force. See problem 1.1. Only if one of the objects is the Earth does the gravitational force matter. And even in that case, it is quite remarkable that the electric forces between the molecules in, say, a wooden board that you might be standing on can completely balance the gravitational force on you due to the entire Earth. However, this wouldn't be the case if you attempt to stand on a lake, unless it's frozen. If you want to give an object a net charge, a possible way is via the triboelectric effect. If certain materials are rubbed against each other, they can become charged. For example, rubbing wool and Teflon together causes the wool to become positively charged and the Teflon negatively charged. The mechanism is simple. The Teflon simply grabs electrons from the wool. The determination of which material ends up with the extra electrons depends on the electronic structure of the molecules in the materials. It turns out that actual rubbing isn't necessary. Simply touching and separating the materials can produce an imbalance of charge. Triboelectric effects are mitigated by humid air because the water molecules in the air are inclined to give or receive electrons depending on which of these actions neutralizes the object. This is due to the fact that water molecules are polar, that is, they are electrically lopsided. Polar molecules will be discussed in Chapter 10. The electrical breakdown of air occurs when the electric field reaches a strength about 3 times 10 to the 6 volts per meter. In fields this strong, electrons are ripped from the molecules in the air. They are then accelerated by the field and collide with other molecules, knocking electrons out of these molecules and so on in a cascading process. The result is a spark, because eventually the electrons will combine in a more friendly manner with molecules and drop down to a lower energy level, emitting the light that you see. If you shuffle your feet on a carpet and then bring your finger close to a grounded object, you will see a spark. The electric field near the surface of the Earth is about 100 volts per meter, pointing downward. You can show that this implies a charge of minus 5 times 10 to the 5 C on the Earth. The atmosphere contains roughly the opposite charge, so that the Earth plus atmosphere system is essentially neutral, as it must be. And then it asks why, and I guess because if it wasn't, then we'd either be heating up or cooling down. If there were no regenerative process, charge would leak between the ground and the atmosphere, and they would neutralize each other in about an hour. But there is a regenerative process, lightning. This is a spectacular example of electrical breakdown. There are millions of lightning strikes per day over the surface of the Earth, the vast majority of which transfer negative charge to the Earth. A lightning strike is the result of the strong electric force, or the electric field, that is produced by the build-up, or rather the separation, of charge in a cloud. This separation arises from the charge carried on moving raindrops, although the exact process is rather complicated. See the interesting discussion in Chapter 9 of Feynman et al., 1977. Lightning can also arise from the charge carried on dust particles in coal mines, flour mills, grain storage facilities, etc. The result can be a deadly explosion. A more gentle form of electrical breakdown is corona discharge. Near the tip of a charged pointy object, such as a needle, the field is large, but then falls off rapidly. You can model the needle roughly as having a tiny charged sphere on its end. Electrons are ripped off the needle, or off the air molecules, very close to the needle, but the field further away isn't large enough to sustain the breakdown, so there is a slow leakage instead of an abrupt spark. This leakage can sometimes be seen as a faint glow. Examples are St. Elmo's fire at the tips of ship masts and a glow at the tips of airplane wings. Yeah, right. There's your chapter summary. It's a whole bunch of equations. And then we've got our famous problems. Man, there's a lot of work to do if you wanted to really engage with this book. I don't think I'm ready for it. I think I need to buttress my mathematics. I'll come back to this maybe one day. The electric potential overview. The first half of this chapter deals mainly with the potential associated with an electric field. The second half covers a number of mathematical topics that will be critical in our treatment of electromagnetism. The potential difference between 2 points is defined to be the negative line integral of the electric field. Equivalently, the electric field equals the negative gradient of the potential. Just as the electric field is the force per unit charge, the potential is the potential energy per unit charge. We give a number of examples involving the calculation of the potential due to a given charge distribution. One important example is the dipole, which consists of two equal and opposite charges. We will have much more to say about the application of dipoles in chapter 10. Line integral of the electric field, potential difference and the potential function, gradient of a scalar function, derivation of the field from the potential, potential of a charge distribution, uniformly charged disk, dipoles, calculation of phi and E, the shapes of the curves, divergence of a vector function, Gauss's theorem and the differential form of Gauss's law, the divergence in Cartesian coordinates, the Laplacian, Laplace's equation, distinguishing the physics from the mathematics. In the preceding section, we have been concerned with mathematical relations and new ways of expressing familiar facts. It may help to sort out physics from mathematics and law from definition if we try to imagine how things would be if the electric force were not a pure inverse square force, but instead a force with a finite range, for instance, a force varying like this. Then Gauss's law in the integral form expressed in equation 250 would surely fail, for by taking a very large surface enclosing some sources, we would find a vanishingly small field on this surface. The flux would go to zero as the surface expanded rather than remain constant. However, we should still define a field at every point in space. We could calculate the divergence of that field, and equation 251, which describes a mathematical property of any vector field, would still be true. Is there a contradiction here? No, because equation 252 would also fail. The divergence of the field would no longer be the same as the source density. We can understand this by noting that a small volume empty of sources could still have a net flux through it owing to the effect of a source outside of the volume if the field has finite range. As suggested in figure 228, more flux would enter the side near the source than would leave the volume. The curl of a vector function, Stokes's theorem, the curl in Cartesian coordinates, the physical meaning of the curl. The name curl reminds us that a vector field with a non-zero curl has circulation or vorticity. Maxwell used the name rotation, and in German a similar name is still used, abbreviated rot. Imagine a velocity vector field G and suppose that curl G is not zero. Then the velocities in this field have something of this character. Got some arrows there. All right, we're up to applications again. Chapter summary, problems. You get the feeling like you'd learn an awful lot if you work through all of those problems. Here are the exercises, which are the problems that don't come with solutions. Electric fields around conductors. In the first two chapters, we were concerned with the electric field and potential due to charges whose positions were fixed and known. We will now study the field and potential due to charges on conductors where the charges are free to move around. This is a more difficult task because on one hand, we need to know the field to determine the positions of the charges, but on the other hand, we need to know the position of the charges to determine the field. Fortunately, there are some facts and theorems that make this tractable, and indeed, in some cases, trivial. The most important fact is that an electrostatic setup, the most important fact is that in an electrostatic setup, the electric field inside the material of a conductor is zero. Equivalently, all points in a given conductor have the same potential. This leads to the somewhat surprising effect called electrical shielding. The electric field inside an empty conducting shell is zero, independent of whatever arbitrary charge distribution exists outside. We prove the very helpful uniqueness theorem, which states that, given the values of the potential phi on the surfaces of a set of conductors, the solution for phi through that space is unique. This theorem often makes things so easy that you may wonder if you're actually cheating. A byproduct of the theorem is the topic of image charges, which allows us to construct the electric field near conductors in certain cases. We define the capacitance coefficients of a set of conductors. These tell us how much charge resides on a conductor at a given potential. Capacitors are a fundamental circuit element, as we will see in Chapter 8. Finally, we discuss the energy stored in a capacitor. Conductors and insulators. Conductors in the electrostatic field. The general electrostatic problem and the uniqueness theorem. Image charges. About the simplest system in which the mobility of the charges in the conductor makes itself evident is the point charge near a conducting plane. Capacitance and capacitors. Potentials and charges on several conductors. Energy stored in a capacitor. Other views of the boundary value problem. Applications, chapter summary, problems. Chapter 4, electric currents. In this chapter, we discuss charge in motion or electric current. The current density is defined as the current per cross-sectional area. It is related to the charge density by the continuity equation. In most cases, the current density is proportional to the electric field. The constant of proportionality is called the conductivity, with the inverse of the conductivity being the resistivity. Ohm's law gives an equivalent way of expressing this proportionality. We show in detail how the conductivity arises on a molecular level by considering the drift velocity of the charge carriers when an electric field is applied. We then look at how this applies to metals and semiconductors. In a circuit, an electromotive force, EMF, drives the current. A battery produces an electromotive force by means of chemical reactions. The current in a circuit can be found either by reducing the circuit via the series and parallel rules for resistors or by using Kirchhoff's rules. The power dissipated in a resistor depends on the resistance and the current passing through it. Any circuit can be reduced to a Thevenin equivalent circuit involving one resistor and one electromotive force source. We end the chapter by investigating how the current changes in an RC circuit. Electric current and current density. Steady currents and charge conservation. Electrical conductivity and Ohm's law. The physics of electrical conduction, currents and ions. Motion in zero electric fields. Motion in non-zero electric field. Types of materials. Conduction in metals. Semiconductors. Circuits and circuit elements. Energy dissipation in current flow. Electromotive force and the voltaic cell. Networks with voltage sources, applying Kirchhoff's rules. Thevenin's theorem. Variable currents in capacitors and resistors. Applications. Chapter summary. Problems. Exercises. Chapter 5. Fields of moving charges. The goal of this chapter is to show that when relativity is combined with our theory of electricity, a necessary conclusion is that a new force, the magnetic force, must exist. In non-static situation, charge is defined via a surface integral. With this definition, charge is invariant, that is, independent of reference frame. Using this invariance, we determine how the electric field transforms between two frames. We then calculate the electric field due to a charge moving with constant velocity. It does not equal the spherically symmetric Coulomb field. Interesting field patterns arise in cases where a charge starts or stops. The main result of this chapter, derived in section 5.9, is the expression for the force that a moving charge or a group of moving charges exerts on another moving charge. On our journey to this result, we will consider setups with increasing complexity. More precisely, in calculating the force on a charge Q due to another charge capital Q, there are four basic cases to consider depending on the charge's motions. 1. If both charges are stationary in a given frame, then we know from chapter 1 that Coulomb's law gives the force. 2. If the source capital Q is moving and lower q is at rest, then we can use the transformation rule for the electric field mentioned above. 3. If the source Q is at rest and lowercase q is moving, then we can use the transformation rule for the force presented in Appendix G to show that the Coulomb field gives the force, as you would expect. 4. Finally, the case we are most concerned with, if both charges are moving, then we will show in section 5.9 that a detailed consideration of the relativistic effects implies that there exists an additional force that must be added to the electrical force. This is the magnetic force. Fascinating. Measurement of charge in motion. Invariance of charge. Electric field measured in different frames of reference. Field of a point charge moving with constant velocity. Field of a charge that starts or stops. Force on a moving charge. Interaction between a moving charge and other moving charges. Chapter summary. Problems. Exercises. The magnetic field. Having shown in Chapter 5 that the magnetic force must exist, we will now study the various properties of the magnetic field and show how it can be calculated for an arbitrary steady current distribution. The Lorentz force gives the total force on a charged particle as F equals QE plus QV times B. The results from the previous chapter give us the form of the magnetic field due to a long straight wire. This form leads to Ampere's law, which relates the line integral of the magnetic field to the current enclosed by the integration loop. It turns out that Ampere's law holds for a wire of any shape. When supplemented with a term involving changing electric fields, this law becomes one of Maxwell's equations, as we will see in Chapter 9. The sources of magnetic fields are currents, in contrast with the source of electric fields, which are charges. There are no isolated magnetic charges or monopoles. This statement is another of Maxwell's equations. As in the electric case, the magnetic field can be obtained from a potential, but it is now a vector potential. Its curl gives the magnetic field. The Biot-Savart law allows us to calculate, in principle, the magnetic field due to any steady current distribution. One distribution that comes up often is that of a solenoid, a coil of wire, whose field is essentially constant inside and zero outside. This field is consistent with an Ampere's law calculation of the discontinuity of B across a sheet of current. By considering various special cases, we derive the Lorentz transformation of the electric and magnetic fields. The electric or magnetic field in one frame depends on both the electric and magnetic fields in another frame. The Hall effect arises from the QV times B part of the Lorentz force. This effect allows us, for the first time, to determine the sign and charge carriers, the sign of the charge carriers in a current. Definition of the magnetic field. Some properties of the magnetic field. Vector potential. Field of any current carrying wire. Fields of rings and coils. A change in B at a current sheet. How the fields transform. Rowland's experiment. Electrical conduction in a magnetic field, the Hall effect. Applications. Chapter summary. Problems. Exercises. Chapter 7, Electromagnetic Induction. In this chapter, we study the effects of magnetic fields that change with time. Our main result will be that a changing magnetic field causes an electric field. We begin by using the Lorentz force to calculate the electromotive force around a loop moving through a magnetic field. We then make the observation that this EMF can be written in terms of the rate of change of the magnetic flux through the loop. The sign of the induced EMF is determined by Lenz's law. If we shift frames so that the loop is now stationary and the source of the magnetic field is moving, we obtain the same result for the EMF in terms of the rate of change of flux as expected. Faraday's law of induction states that this result holds independent of the cause of the flux change. For example, it applies to the case in which we turn a dial to decrease the magnetic field while keeping all objects stationary. The differential form of Faraday's law is one of Maxwell's equations. Mutual inductance is the effect by which a changing current in one loop causes an EMF in another loop. This effect is symmetrical between the two loops, as we will prove. Self-inductance is the effect by which a changing current in a loop causes an EMF in itself. The most commonly used object with self-inductance is a solenoid, which we call an inductor, symbolized by L. The current in an RL circuit changes in a specific way, as we will discover. The energy stored in an inductor equals Li squared on 2, which parallels the CV squared on 2 energy stored in a capacitor. Similarly, the energy density in a magnetic field equals B squared divided by 2 mu 0, which parallels the epsilon 0 E squared on 2 energy density in an electric field. Faraday's discovery. Michael Faraday's account of the discovery of electromagnetic induction begins as follows. 1. The power which electricity of tension possesses of causing an opposite electrical state in its vicinity has been expressed by the general term induction, which, as it has been received into scientific language, may also, with propriety, be used in the same general sense to express the power which electrical currents may possess of inducing any particular state upon matter in their immediate neighborhood, otherwise indifferent. It is with this meaning that I purpose using it in the present paper. 2. Certain effects of the induction of electrical currents have already been recognized and described, as those of magnetization, Ampere's experiments of bringing a copper disc near to a flat spiral, his repetition with electromagnets of Arago's extraordinary experiments, and perhaps a few others. Still, it appeared unlikely that these could be all the effects which induction by currents could produce, especially as, upon dispensing with iron, almost the whole of them disappear, whilst yet an infinity of bodies, exhibiting definite phenomena of induction with electricity of tension, still remain to be acted upon by the induction of electricity in motion. 3. Further, whether Ampere's beautiful theory were adopted, or any other, or whatever reservation were mentally made, still it appeared very extraordinary that as every electric current was accompanied by a corresponding intensity of magnetic action at right angles to the current, good conductors of electricity, when placed within the sphere of this action, could not have any current induced through them, or some sensible effect produce equivalent in force to such a current. 4. These considerations, with their consequence, the hope of obtaining electricity from ordinary magnetism, have stimulated me at various times to investigate experimentally the inductive effect of electric currents. I lately arrived at positive results, and not only had my hopes fulfilled, but obtained a key which appeared to me to open out a full explanation of Arago's magnetic phenomena, and also to discover a new state which may probably have great influence in some of the most important effects of electric currents. 5. These results I purpose describing, not as they were obtained, but in such a manner as to give the most concise view of the whole. This passage was part of a paper Faraday presented in 1831. It is quoted from his Experimental Researches in Electricity, published in London in 1839. There follows in the paper a description of a dozen or more experiments through which Faraday brought to light every essential feature of the production of electric effects by magnetic action. By electricity of tension, Faraday meant electrostatic charges, and the induction he refers to in the first sentence involves nothing more than we have studied in Chapter 3, that the presence of a charge causes a distribution of charges on conductors nearby. Faraday's question was, why does an electric current not cause another current in nearby conductors? Conducting rod moving through a uniform magnetic field. Loop moving through a non-uniform magnetic field. Stationary loop with the field source moving. Universal law of induction. mutual inductance, a reciprocity theorem, self-inductance, circuit containing self-inductance, energy stored in the magnetic field, chapter summary, problems, exercises, alternating current circuits. In earlier chapters, we encountered resistors, capacitors, and inductors. We will now study circuits containing all three of these elements. If such a circuit contains no EMF source, the current takes the form of a decaying oscillation in the case of small damping. The rate of decay is described by the Q factor. If we add on a sinusoidally oscillating EMF source, then the current will reach a steady state and with the same frequency of the oscillation as the EMF source. However, in general, there will be a phase difference between the current and the EMF. This phase, along with the amplitude of the current, can be determined by three methods. The first method is to guess a sinusoidal solution to the differential equation representing Kirchhoff's loop equation. The second is to guess a complex exponential solution and then take the real part to obtain the actual current. And the third is to use complex voltages, currents, and impedances. These complex impedances can be combined by the same series and parallel rules that work for resistors. As we will see, the third method is essentially the same as the second method, but with better bookkeeping. This makes it far more tractable in the case of complicated circuits. Finally, we derive an expression for the power dissipated in a circuit, which reduces to the familiar V squared on R result of the circuit if the circuit is purely resistive. A resonant circuit, alternating current, RL circuit, RC circuit, transients, RLC circuit, width of the I0 omega curve, complex exponential solutions, alternating current networks, admittance and impedance, power and energy in alternating current circuits, applications, chapter summary, problems, exercises. Chapter 9, Maxwell's equations and electromagnetic waves. In the course of our study of electromagnetism, we have been gradually putting together the pieces of the puzzle of Maxwell's equations. In this chapter, we find the final piece, known as the displacement current. We do this by exposing a contradiction in our present theory and then resolving it. Once we write down the full set of Maxwell's equations, we quickly discover that in vacuum they lead to wave solutions with a set of specific properties. These waves are light waves, and unlike other waves you are familiar with, they require no medium to support their propagation. Traveling electromagnetic waves carry energy, and more generally, the Poynting vector describes the energy flow in an arbitrary electromagnetic field. Standing electromagnetic waves, which are the superposition of traveling waves, carry no net energy. By examining how the electric and magnetic fields transform between frames, we find that a light wave in one frame looks like a light wave in any other frame. Something is missing. The displacement current, Maxwell's equations, an electromagnetic wave, other waveforms, superposition of waves, energy transport by electromagnetic waves, power density, the Poynting vector, how a wave looks in a different frame, applications, chapter summary, problems, exercises. Chapter 10, Electric Fields in Matter. Overview. In this chapter, we will study how electric fields affect and are affected by matter. We concern ourselves with insulators, or dielectrics, characterized by a dielectric constant. The study of electric fields in matter is largely the study of dipoles. We discussed these earlier in chapter 2, but we will derive their properties in more generality here, showing in detail how the multipole expansion comes about. The net dipole moment induced in matter by an electric field can come about in two ways. In some cases, the electric field polarizes the molecules. The atomic polarizability quantifies this effect. In other cases, a molecule has an inherent dipole moment, and the external field serves to align these moments. In any case, a material can be described by a polarization density P. The electric susceptibility gives up to a factor of epsilon 0, the ratio of P to the electric field. The effect on the polarization density is to create a surface charge density on a dielectric material. This explains why the capacitance of a capacitor is increased when it is filled with a dielectric. The surface charge on the dielectric partially cancels the free charge on the capacitor plates. We study the special case of a uniformly polarized sphere, which interestingly has a uniform electric field in its interior. We then extend this result to the case of a dielectric sphere placed in a uniform electric field. By considering separately the free charge and bound charge, we are led to the electric displacement vector D, whose divergence involves only the free charge, unlike the electric field, whose divergence involves all the charge, by Gauss's law. We look at the effects of temperature on the polarization density and how the polarization responds to rapidly changing fields, and how the bound charge current affects the curl B Maxwell equation. Finally, we consider an electromagnetic wave in a dielectric. We find that only a slight modification to the vacuum case is needed. Dielectrics. The moments of a charge distribution, the potential and field of a dipole, the torque and the force on a dipole in an external field, atomic and molecular dipoles induce dipole moments, permanent dipole moments, the electric field caused by polarized matter, the field outside matter, the field inside matter, another look at the capacitor, the field of a polarized sphere, a dielectric sphere in a uniform field, the field of a charge in a dielectric medium and Gauss's law, a microscopic view of the dielectric, polarization in changing fields, the bound charge current, an electromagnetic wave in a dielectric, applications, chapter summary, problems, exercises. Chapter 11, Magnetic Fields in Matter. Magnetic fields in matter are a bit more involved than electric fields in matter. Our main goal in this chapter is to understand the three types of magnetic materials: diamagnetic materials, which are weakly repelled by a solenoid, paramagnetic materials, which are somewhat strongly attracted, and ferromagnetic materials, which are very strongly attracted. As was the case in Chapter 10, we will need to understand dipoles. The far field of a magnetic dipole has the same form as that of an electric dipole, with the magnetic dipole moment replacing the electric dipole moment. However, the near fields are fundamentally different due to the absence of magnetic charge. We will find that diamagnetism is due to the fact that an applied magnetic field causes the magnetic dipole moment arising from the orbital motion of electrons in atoms to pick up a contribution pointing opposite to the applied field. In contrast, in the case of paramagnetism, the spin dipole moment is the relevant one, and it picks up a contribution pointing in the same direction as the applied field. Ferromagnetism is similar to paramagnetism, although a certain quantum phenomenon makes the overall effect much larger. A ferromagnetic dipole moment can exist in the absence of an external magnetic field. Magnetized materials can be described by the magnetization M, the curl of which gives the bound currents which arise from both orbital motion and spin. By considering separately the free and bound currents, we are led to the field H, also called the magnetic field, whose curl involves only the free current, unlike the magnetic field B, whose curl involves all the current by Ampere's law. How various substances respond to a magnetic field. The absence of magnetic charge. The field of a current loop. The force on a dipole in an external field. Electric currents in atoms. Electron spin and magnetic moment. Magnetic susceptibility. The magnetic field caused by magnetized matter. The field of a permanent magnet. Free currents in the field H. Ferromagnetism. Applications. Chapter summary. Problems. Exercises. Chapter 12. Solutions to the problems. All right, well, this is basically the end of the book. We'll have a look at the appendices though, huh? All right, so we're up to Appendix A, differences between SI and Gaussian units. In this appendix, we discuss the difference between the SI and Gaussian system of units. First, we'll look at the units in each system, and then we will talk about the clear and not so clear ways in which they differ. SI units, Gaussian units, main differences between the systems, 3 units versus 4, the definition of B, rationalized units. Appendix B, SI units of common quantities. Okay, Newton, joule, ampere, volt. Okay, there's a whole lot of... Okay. Appendix C, unit conversions. Okay. Derivations, force, Newton versus dyne, energy, joule versus erg, ERG, I don't know that expression. Charge, Coulomb versus ASU. SI and Gaussian formulas, eliminating, that's the permittivity of free space and the permeability of free space, I believe. Don't know really what that means. Changing B to B on C. Other definitional differences. The formulas. Oh, wow. Wow. That's non-trivial, isn't it? Appendix E, exact relations among SI and Gaussian units. Appendix F, curvilinear coordinates. We begin this appendix by listing the main vector operators, gradient, divergence, curl, Laplacian, in Cartesian, cylindrical, and spherical coordinates. We then talk a little about each operator, define things, derive a few results, give some examples, etc. You will note that some of the expressions below are rather scary looking. However, you won't have to use their full forms in this book. In the applications that come up, invariably only 1 or 2 of the terms in the expression are non-zero. Wow. Cylindrical coordinates, spherical coordinates, gradient, Cartesian gradient, spherical gradient, divergence, cylindrical divergence, first method, cylindrical divergence, second method, curl, cylindrical curl, first method, cylindrical curl, second method, Laplacian, cylindrical Laplacian, exercises. Appendix G, a short review of special relativity. Foundations of relativity. We assume that the reader has already been introduced to special relativity. Here we shall review the principal ideas and formulas that are used in the text beginning in Chapter 5. Most essential is the concept of an inertial frame of reference for space-time events that the transformation of the coordinates of an event from one inertial frame to another. A frame of reference is a coordinate system laid out with measuring rods and provided with clocks. Clocks are everywhere. When something happens at a certain place, the time of its occurrence is read from a clock that was at and stays at that place. That is, time is measured by a local clock that is stationary in the frame. The clocks belonging to the frame are all synchronized. One way to accomplish this, not the only way, was described by Einstein in his great paper of 1905. Light signals are used. From a point A at time ta, a short pulse of light is sent out toward a remote point B. It arrives at B at the time tb, as read on a clock at B, and is immediately reflected back toward A, where it arrives at T prime A. If TB equals TA plus T prime A, divided by 2, the clocks at A and B are synchronized. If not, one of them requires adjustment. In this way, all clocks in the frame can be synchronized. Note that the job of observers in this procedure is merely to record local clock readings for subsequent comparison. An event is located in space and time by its coordinates x, y, z, and t in some chosen reference frame. The event might be the passage of a particle at time t1 through the space point x1, y1, z1. The history of the particle's motion is a sequence of such events. Suppose the sequence has the special property that x equals vxt and y equals vyt and z equals vzt at every time t, with vx, vy, vz constant. That describes motion in a straight line at constant speed with respect to this frame. An inertial frame of reference is a frame in which an isolated body, free from external influences, moves in this way. An inertial frame, in other words, is one in which Newton's first law is obeyed. Behind all of this, including the synchronization of the clocks, are two assumptions about empty space. It is homogeneous, that is, all locations in space are equivalent, and it is isotropic, that is, all directions in space are equivalent. Two frames, let us call them F and F prime, can differ in several ways. One can simply be displaced with respect to the other, the origin of coordinates in F prime being fixed at a point in F that is not at the F coordinate origin, or the axes in F prime might not be parallel to the axes in F. As for the timing of events, if F and F prime are not moving with respect to one another, a clock stationary in F is stationary also in F prime. In that case, we can set all F prime clocks to agree with F clocks and then ignore the distinction. Differences in frame location and frame orientation only have no interesting consequences if space is homogeneous and isotropic. Suppose now that the origin of frame F is moving relative to the origin of frame F prime is moving relative to the origin of frame F. The description of a sequence of events by coordinate values and clock times in F can differ from the description of the same events by space coordinate values in F prime and times measured by clocks in F prime. How must the two descriptions be related? In answering that, we shall be concerned only with the case in which F is an inertial frame and F prime is a frame that is moving relative to F at constant velocity and without rotating. In that case, F prime is also an inertial frame. Special relativity is based on the postulate that physical phenomena observed in different inertial frames of reference appear to obey exactly the same laws. In that respect, one frame is as good as another. No frame is unique. If true, this relativity postulate is enough to determine the way a description of events in one frame is related to the description in a different frame of the same events. In that relation, there appears a universal speed, the same in all frames, whose value must be found by experiment. Sometimes added as a second postulate is the statement that a measurement of the velocity of light in any frame of reference gives the same result whether the light source is stationary in that frame or not. One may regard this as a statement about the nature of light rather than an independent postulate. It asserts that electromagnetic waves in fact travel with the limiting speed applied by the relativity postulate. The deductions from the relativity postulate, expressed in the formulas of special relativity, have been precisely verified by countless experiments. Nothing in physics rests on firmer foundation. Lorentz transformations. Consider two events, A and B, observed in an inertial frame of reference F. Observed in this usage is short for whose space-time coordinates are determined with the measuring rods and clocks of frame F. Remember that our observers are equipped merely with pencil and paper, and we must post an observer at the location of every event. The displacement of one event from the other is given by the four numbers xb minus xa, yb minus ya, zb minus za, and tb minus ta. The same two events could have been located by giving their coordinates in some other frame f prime. Suppose f prime is moving with respect to f in the manner indicated in figure G1. The spatial axes of f prime remain parallel to those in f, while, as seen from f, the frame f prime moves with speed v in the positive x direction. This is a special case, obviously, but it contains most of the interesting physics. Event A, as observed in f prime, occurred at x prime A, y prime A, z prime A, t prime A. The last of these numbers being the reading of a clock belonging to, that is, stationary in, f prime. The space-time displacement, or interval, between events A and B in f prime is not the same as in f. Its components are related to those in f by the Lorentz transformation. Okay. In these equations, c is the speed of light, b equals v on c, and gamma equals 1 on the square root of 1 minus beta squared. The inverse transformation has a similar appearance as it should if no frame is unique. It can be obtained from equation G2 simply by exchanging primed and unprimed symbols and reversing the sign of beta, as you can verify by explicitly solving for the quantities xb minus xa and tb minus ta. Two events, A and B, are simultaneous in f if tb minus ta equals 0. But that does not make t prime minus t prime a equals 0 unless xb equals xa. Thus, events that are simultaneous in one inertial frame may not be so in another. Do not confuse this fundamental relativity of simultaneity with the obvious fact that an observer not equally distant from two simultaneous explosions will receive light flashes from them at different times. The times t prime a and t prime b are recorded by local clocks at each event, clocks stationary in f prime that have previously been perfectly synchronized. Consider a rod stationary in f prime that is parallel to the x prime axis and extends from x prime a to x prime b. Its length in f prime is just x prime b minus x prime a. The rod's length, as measured in frame f, is the distance xb minus xa between 2 points in the frame f that its ends pass simultaneously according to clocks in f. For these two events, then, tb minus ta equals 0. With this condition, the first of the Lorentz transformation equations gives us at once this expression in G3. Okay. This is the famous Lorentz contraction. Loosely stated, lengths between fixed points in f prime, if parallel to the relative velocity of the frames, are judged by observers in f to be shorter by a factor of 1 on gamma. This statement remains true if f prime and f are interchanged. Lengths perpendicular to the relative velocity measure the same in the two frames. Here we've got figure G1. Two frames moving with relative speed v. The E is stationary in frame F. The L is stationary in frame F prime. In this example, beta equals V on C equals 0.866. Gamma equals 2. A, where everything was, as determined by observers in F, at a particular instant of time t, according to clocks in F. B, where everything was, as determined by observers in F prime, at a particular instance of time, according to clocks in F prime. Question. Suppose the clocks in the two frames happen to be set so that the left edge of the E touched the left edge of the L at t equals 0 according to a local clock in F, and at t prime equals 0 according to a local clock in F prime. Let the distances be in feet and take c as 1 foot per nanosecond. What is the reading t of all the f clocks in A? What is the reading t prime of all the f prime clocks in B? Answer, t equals 4.62 nanoseconds and t prime equals 4.04 nanoseconds. If you don't agree, study the example again. Oh man, I'm not going to think hard about that. Consider one of the clocks in f prime. It is moving with speed v through the frame f. Let us record as t prime a its reading as it passes one of our local clocks in f. The local clock reads at that moment TA. Later, this moving clock passes another F clock. At that event, the local F clock reads TB, and the reading of the moving clock is recorded as T prime B. The two events are separated in the F frame by a distance of XB minus XA equals V times TB minus TA. Substituting this into the fourth equation of the Lorentz transformation in equation G2, we obtain equation G4. According to the moving clock, less time has elapsed between the two events than is indicated by the stationary clocks in F. This is the time dilation that figures in the twin paradox. It has been verified in many experiments, including one in which an atomic clock was flown around the world. Remembering that moving clocks run slow by the factor 1 on gamma, and that moving graph paper is shortened parallel to its motion by the factor 1 on gamma, you can often figure out the consequences of a Lorentz transformation without writing out the equations. This behavior, it must be emphasized, is not a peculiar physical property of our clocks and paper, but is intrinsic in space and time measurement under the relativity postulate. All right, then we've got velocity addition, energy, momentum, and force. And then we're done. Appendix H, radiation by an accelerated charge. A particle with charge q has been moving in a straight line at constant speed v0 for a long time. It runs into something, let us imagine, and in a short period of constant deceleration, the duration tau, the particle is brought to rest. The graph of velocity versus time in figure H1 describes its motion. What must the electric field of this particle look like after that? Figure H2 shows how to derive it. Exercises. Appendix I, superconductivity. The metal lead is a moderately good conductor at room temperature. Its resistivity, like that of other pure metals, varies approximately in proportion to the absolute temperature. As a lead wire is cooled to 15 Kelvin, its resistance falls to about 1/20th of its value at room temperature, and the resistance continues to decrease as the temperature is lowered further. But as the temperature 7.22 Kelvin is passed, there occurs, without forewarning, a startling change. The electrical resistance of the lead wire vanishes. So small does it become that a current flowing in a closed ring of lead wire colder than 7.22 Kelvin, a current that would ordinarily die out in much less than a microsecond, will flow for years without measurably decreasing. This phenomenon has been directly demonstrated. Other experiments indicate that such a current could persist for billions of years. One can hardly quibble with the flat statement that the resistivity is zero. Evidently, something quite different from ordinary electrical conduction occurs in lead below 7.22 Kelvin. We call it superconductivity. Superconductivity was discovered in 1911 by the great Dutch low-temperature experiment Kamerlingh Ons. He observed it first in mercury, for which the critical temperature is 4.16 Kelvin. Since then, hundreds of elements, alloys, and compounds have been found to become superconductors. Their individual critical temperatures range from roughly a millikelvin up to the highest yet discovered, 138 Kelvin. Curiously, among the elements that do not become superconducting are some of the best normal conductors, such as silver, copper, and the alkali metals. Superconductivity is essentially a quantum mechanical phenomenon, and a rather subtle one at that. The freely flowing electric current consists of electrons in perfectly orderly motion. Like the motion of an electron in an atom, this electron flow is immune to small disturbances, and for a similar reason. A finite amount of energy would be required to make any change in the state of motion. It is something like the situation in an insulator in which all the levels in the valence band are occupied and separated by an energy gap from the higher energy levels in the conduction band. But unlike electrons filling valence band, which must in total give exactly zero net flow, the lowest energy state of the superconducting electrons can have a net electron velocity, hence current flow, in some direction. Why should such a strange state become possible below a certain critical temperature? We can't explain that here. We've got a note here. The abrupt emergence of a state of order at a certain critical temperature reminds us of the spontaneous alignment of electron spins that occurs in iron below its Curie temperature, mentioned in section 1111. Such cooperative phenomena always involve a large number of mutually interacting particles. A more familiar cooperative phenomenon is the freezing of water, also characterized by a well-defined critical temperature. It involves the interaction of the conduction electrons not only with each other, but also with the whole lattice of positive ions through which they are moving. That is why different substances can have different critical temperatures, and why some substances are expected to remain normal conductors right down to absolute zero. In the physics of superconductivity, magnetic fields are even more important than you might expect. We must state at once that the phenomena of superconductivity in no way violate Maxwell's equations. Thus, the persistent current that can flow in a ring or superconducting wire is a direct consequence of Faraday's law of induction, given that the resistance of the ring is really zero. For if we start with a certain amount of flux, phi 0 reading threading the ring, then because the integral of EDS around the ring remains always zero, otherwise there would be infinite current due to the zero resistance, divided T must be zero. The flux cannot change. The current I in the ring will automatically assume whatever value is necessary to maintain the flux at phi 0. Figure I1 outlines a simple demonstration of this and shows how a persistent current can be established in an isolated superconducting circuit. Superconductors can be divided into two types. In type 1 superconductors, the magnetic field inside the material itself, except very near the surface, is always zero. That is not a consequence of Maxwell's equations, but a property of the superconducting state, as fundamental and once as baffling a puzzle as the absence of resistance. The condition B equals zero inside the bulk of a type 1 superconductor is automatically maintained by currents flowing in a thin surface layer. In type 2 superconductors, quantized magnetic flux tubes may exist for a certain range of temperatures and external magnetic field. These tubes are surrounded by vortices of current, essentially little solenoids, which allow the magnetic field to be zero in the rest of the material. Outside the flux tubes, the material is superconducting. A strong magnetic field destroys superconductivity, although type 2 superconductors generally can tolerate much larger magnetic fields than type 1. None of the superconductors known before 1957 could stand more than a few hundred Gauss. That discouraged practical applications of zero resistance conductors. One could not pass a large current through a superconducting wire because the magnetic field of the current itself would destroy the superconducting state. But then a number of type 2 superconductors were discovered that could preserve zero resistance in fields up to 10 Tesla or more. A widely used type 2 superconductor is an alloy of niobium and tin that has a critical temperature of 18 Kelvin, and if cooled to 4 Kelvin, remains superconducting in fields up to 25 Tesla. Type 2 superconducting solenoids are now common in that produce steady magnetic fields of 20 Tesla without any cost in power other than the incident to their refrigeration. Uses of superconductors include magnetic resonance imaging (MRI) machines, which are based on the physics discussed in Appendix J, and particle accelerators. There are also good prospects for the widespread use of superconductors in large electrical machinery, maglev trains, and the long-distance transmission of electrical energy. In addition to the critical magnetic field, the critical temperature is also a factor in determining the large-scale utility of a superconductor. In particular, a critical temperature higher than 77 Kelvin allows relatively cheap cooling with liquid nitrogen, as opposed to liquid helium at 4K. Prior to 1986, the highest known critical temperature was 23 Kelvin. Then a new type of superconductor, a copper oxide, cuprate, was observed with a critical temperature of 30 Kelvin. The record critical temperature was soon pushed to 138 Kelvin. These superconductors are called high-temperature superconductors. Unfortunately, although they are cheaper to cool, their utility is limited because they tend to be brittle and hence difficult to shape into wires. However, in 2008, a new family of high-temperature superconductors was discovered, with iron as a common element. This family is more ductile than cuprates, but the highest known critical temperature is 55 Kelvin. The hope is that this will eventually cross the 77 Kelvin threshold. The mechanism that leads to high-temperature superconductivity is more complex than the mechanism for low-temperature superconductivity. In contrast with the well-established BCS theory, named after Bardeen, Cooper, and Schrieffer, formulated in 1957, for low-temperature superconductors, a complete theory of high-temperature superconductors does not yet exist. All known high-temperature superconductors are type 2, but not all type 2 superconductors are high temperature. Indeed, low-temperature type 2 superconductors, being both ductile and tolerant of large magnetic fields, are the ones presently used in MRI machines and other large-scale applications. At the other end of the scale, the quantum physics of superconductivity makes possible electric measurements of unprecedented sensitivity and accuracy, including the standardization of the volt in terms of an easily measured oscillation frequency. To the physicist, superconductivity is a fascinating large-scale manifestation of quantum mechanics. We can trace the permanent magnetism of the magnet in figure I1 down to the intrinsic magnetic moment of a spinning electron, a kind of supercurrent in a circuit less than 10 to the minus 10 meters in size. The ring of solder wire with the persistent current flowing in it is, in some sense, like a gigantic atom. The motion of its associated electrons, numerous as they are, marshaled into the perfectly ordered behavior of a single quantum state. And we've got Appendix J, magnetic resonance. The electron has angular momentum of spin, J. Its magnitude is always the same, h divided by 4 pi, or 5.273 times 10 to the minus 35 kilograms meter squared per second. Associated with the axis of spin is a magnetic dipole moment, mu, of magnitude 0.9285 times 10 to the minus 3 joules per Tesla. An electron in a magnetic field experiences a torque tending to align the magnetic dipole in the field direction. It responds like any rapidly spinning gyroscope. Instead of lining up with the field, its spin axis precesses around the field direction. Let us see why any spinning magnet does this. Okay. Appendix K, helpful formulas and facts. Integral table, vector identities, Taylor series, complex numbers, trigonometric identities, and here we are, references. Not that many references really, is there? And then the index. And there was some okay, we've got vector operators, Cartesian coordinates, cylindrical coordinates, and spherical coordinates. And that's it. We're through the book. So I'll take you over the farewell cam. We'll wrap up. And that's a wrap. So, yes, that was everything in electricity and magnetism. Some very interesting stuff in there. It's regrettable I haven't got the time to go through it in close detail. And I'm sort of not ready to. I think I really need to improve my calculus before I try and take this on. But I think I'll be returning to this book in the future, so I look forward to that. This is the end of the video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.